Okay, so the home stretch here. Um, Similar to what we did in for the high and low pass, and I guess we don't need this because I wasn't sure. I was reviewing what we had already done as I was after I'd already made this title slide. So, and I suppose we call it a little background as well. It's nothing really different than before, except now we have to deal with combining impedances, background, and I guess, and analysis background maybe. We'll have another one to go over for that. So we're going to be looking at two different RLC circuits. And we've got the okay, the series, and then all of a sudden this is turning red. I don't know why. And I'm moving a toolbar that you guys can't see. Oh my. Oh, finally it was going nutty on me. I don't understand. And let's see, you get this to black. What is this? Dark gray. Let's see what that looks like. Okay, so we have our inductor, and we have our capacitor. Make these a little bigger, so that's a ground symbol, believe it or not. V in, V out. And notice now that it's the delta V of the LC is V out. Now, as we've alluded to in lecture, we define our generalized impedance. Well, we didn't allude to this, but it's, if you think, it's a vector in the polar plane. And so the reactance of an inductor is plus 2 pi FCL, and the reactance of a capacitor is minus 1 over 2 pi FC. And we've already established that they behave in opposite directions. So now we have a situation where we have both the inductor and the capacitor. So the inductor is on the positive imaginary plane, and the capacitor is on the negative. Let's bring it a little bigger. Negative imaginary plane, and the resistor is all on the real plane, and real axis. I said plane, real axis I meant. So what happens is then in this, you see these two are components, and you notice that the C wins in this case. It's larger than the L, and I suppose we'll do it like that. And so you see we can make a resultant that's there, and this will be Z total. And so we have to bring in the good old Pythagorean theorem. So in this case, this is our Z2. and this is our Z1. And as always, V out over V in equals Z2 over Z1 plus Z2. So in the case of, Z2, that's pretty easy. Z2 simply equals, and they're in series, okay, so that would be ZC plus ZL. And when you do impedances, series is always just adding them together. And I think I'll go into this more in lecture. What happens is you can kind of see that since this is 1 over 2 pi FC, when you add them together in series, you end up with the inversion. I mean, you add up two capacitors. But in any event, let's just stick with the task at hand. Now, these are magnitudes. So, and so we don't care about the signs. They're both going to be positive. And no, give me a minute. Let me make sure I'm doing this right. Yeah, that's right. So all we do is well, okay, let's be, so it's minus 1 over 2 pi FC squared, but then square root magnitude, right? So basically this is 1 over 2 pi FC plus 2 pi FL. That's Z2. Now the harder one is Z total. And I want to pause this a second. So I did make a mistake. This is why you don't start doing this without rehearsing it first. Okay, well, it's not a big mistake, but okay, so it is in reality this, but it's minus 1 over 2 pi FC plus 2 pi FL and then you square it and take the square root. And that just means, because this could be negative sometimes, and we need it to be a positive number, that's all. Now, here's the tricky part. Now we need Z1 plus Z2, which is equal to ZR plus ZL plus ZC, but these are vectors. So this becomes ZR squared plus minus 1 over 2 pi FC square, blah, 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 not yet, plus 2 pi FL squared, and then that whole mess is square rooted. And yes, you can, this is called the phase angle, and there is an angle, but we're not going to deal with it this for now. This is just getting ready for this pre-lab kind of stuff. Okay, so let's sort of do our thought experiment here. And what we see now is that so V out over V in equals Z2 over Z1 plus Z2. And Z2 is a series circuit. So, give me a minute. Right. So we know that and so this will be Z. We know that ZC, and this would be log F. This would be the capacitor, and this will be the inductor. So in a series circuit, when we're at low frequency, so at low F, Z of C dominates, and at high F, Z of L dominates. But in both cases, Z2 is greater than Z1, so V out over V in approaches, 1 as going to F, I know how to do it, as F goes to 0. Come on, it's lagging on me. As F goes to 0 or F goes to infinity. So 0, infinity. And you see here that they cross at a certain point. And that is where they're equal to each other. And notice that when they're equal to each other, that then this quantity here where'd it go? So at the crossing point, in principle, then these two are equal to each other. That means Z2 equals 0. And so that means that V out over V in is going to equal 0. So when we make our Bode plot, we're going to see we expect to see something like this. And this is the resonance frequency, it's called. Okay. So we need this. Oh, it's already on the clipboard, it seems. Okay. So that means we can set 1 over 2 pi fc equal to 2 pi fl. And let's see, I want to get f on one side. We'll say, so that becomes 2 pi f squared L equals to 1 over 2 pi C. And then we see that right, so now we can go f squared equals 4 pi squared LC, and 1 over LC, 1 over all that mess. Okay, so f, and we'll call that the resonance frequency, is equal to 2 pi LC square root. Okay. Now, the other circuit we're exploring is the parallel RLC. And in this case, we have a resistor once again. But now we have the inductor and the capacitor in parallel. And this is still Z2, and this is still Z1. Now, Z2, now when they're in parallel, 1 over ZC plus 1 over Z L. So now it becomes minus I'm going to be careful here. Minus 2 pi FC plus 1 over 2 pi FL. So these are inverted, so this is still 1 over Z2. So now we add those two together, and let's see, we add them together and square root them again, right? No, add them in quadrature. So isn't that, in this case, isn't that the same as getting the absolute value of the sum. Well, let's make sure. I8. Oh, yeah, ZLC in parallel. Ah, got it. I see. We should go in too fast there. Okay, where'd it go? Right. But let's table this for a minute. So we have ZC and ZL as our common denominator. So we have ZL plus ZC equals 1 over Z2. And so Z2 equals ZC times ZL divided by ZL plus ZC. And so this is minus 1 over 2 pi FC times 2 pi FL divided by 2 pi FL minus 1 over 2 pi FC. And if we let's see, if we have 2 minus 3 squared square root, what do we get? Minus 1 square root 1. Yeah, so it's the absolute value. Let's try another one. 2 minus 4 is minus, so minus, yeah, so it's absolute value. Okay. So we can just do absolute value of this mess. And yeah, there it is. It's not very big. So I'm going to go over this again, this spreadsheet for everybody. Okay, view. And so, yeah, Z L times ZC, and then ZL minus ZC. Well, they're added, right? But it happens to be that it's negative 1 over 2 pi. Okay. And in here, I dropped the minus sign. 1 over 2 pi FC. Okay, we'll get back to that. So, now what you see is that the combined resistance, let's think about this right now. I've said this before in class, and I told you to remember it. I don't know. So, in a parallel circuit, the low Z dominates, or the low R. Because as one of these gets smaller and smaller, then the current will just flow through that one. It will just ignore the other one. So what that means is then Z2 over Z1 plus Z2, Z2 goes low. Okay, Z2 is dominated at low F by the Z of the inductor, and it's dominated at high F by the Z of the capacitor. In either case, now Z2 is less or much less than Z1 at high and low, or as F goes to 0 or F goes to infinity. So now what we expect is that log F and V out over V in. So if Z2, so that means then that V out over V in goes to 0. And once again, though, at some point when neither one of them dominates, so there's no domination when ZC equals ZL. And once again, this is the resonance condition, but we see that it looks at the opposite now. So we get at the resonance frequency, we get the highest output instead of the lowest input. Okay, so that's our background, and we'll go into more when we do some analysis. All right. So, right, so you see, oh, wrong one. But anyways, this is the impedances of each one. That's something I'm going to have you make for the now the final logbook. Okay, but let's go here. All right, so there's the data points. This is your data table. Maybe you've already typed it into a spreadsheet, so it's up to you whether you want to copy paste. Let's see here. I did it on here for previous background, but let's start with the series. And I've got the phase angle in there, but we'll ignore that for the time being. So there's some values here. At some point, you're going to type in the values that for your data. Remember, you're supposed to record that. And first thing we're going to do is we're going to calculate the, the resonance frequency. All right, so I'm going to save. This is, wait a minute, so I need to save this as the template File, save as. Let's think about this. Well, maybe I'll just stick with it as it is for now. Okay, so the resonance frequency, remember, is 1 over 2 pi square root of LC. And you see it's about 6,200. And so what I've done is, this is the data table you had, but what I've done here is now I've made this, it says equals to that, H2 in this case. All right. Now, we want to plot, eventually during the analysis, we want to plot and let's see, this here, phase angle, that'll be analysis. So I'll leave that, but I'm going to clear these. So anyways, here's a little cleverness. Well, I guess maybe it's better to call this the resonance frequency. F-res. There we go. And all I just did was say is equal to H2, but I notice I put the dollar signs, and then you can use the fill handle to drag it down. And now, and you may be able to just simply copy paste this from your other spreadsheet. So there we got 2 pi FC, because C8 is the frequency, D4 is the capacitance. Don't forget the dollar signs. Fill. And then the resistor is just constant. And in this case, we used 100 ohms. And of course, fill it. And then the inductor is 2 pi times the frequency times the inductance value. And notice that we've added this extra term for the resistance of the inductor. Now, we didn't measure it, but we're just including it there. And I'll explain why. Well, one reason is that it's real. Every inductor, the ideal inductor, has a resistance of 0, but that's not possible in the real world. So every inductor has some small resistance left to it. And I suppose we could change that to a number just to, it looks weird as scientific. It makes it look large when it's not. There we go, 1 ohm. And this one could be a number too, I suppose. And right here, you know, you could do that too, but it would be like lots of leading zeros. Then you'd have to add some conversion factor in here, but I just kept it in Henrys and farads, so scientific notation works best. So, see, this is 10 to the minus 7, so that's tenths of a microfarad, which is 900 nanofarads. That's what your label says, 900 something. Okay, so V out over V in is just that crazy looking thing from before. And so the Z of the inductor minus Z of the capacitor, square it and square root it. Oh, that's here. And then I just copy pasted this part and then added the Z of the resistor. Notice there are no dollar signs because I'm picking up the values out of these columns here. Okay. And then, of course, the fill handle. And then see that now I just took the logarithm of it. 20 times the logarithm. All right. Now, of course, you can type in your data. And remember 20 log of this guy here. Okay, so let's go to 100%. And we'll put this to the side for now. So there's my graph. So let's just go through it. We have the frequency, and now we hold down the control key. And we say insert chart, and we're going to scatter plot. And that is looking, oh, of course, because I have log f, a log of the output, v out over v in, but I need to make this one logarithm. And I just jazzed it up by, there we go. Okay, so, yeah, and so, well, some of you have data, some of you don't. So when you have data, you can go to select data here and add your data, the frequencies, and the log of the V out, 20 log V out over V in. What else? Oh, so I'll show you why we need this. If I make it 0, you're going to see that it complains because V out over V in becomes 0, and because at resonance the Z2 is equal to 0. But there's always a little bit of, I could put a ½ an ohm in there. And then, so part of the analysis is we're going to add a 3 dB line and then take the width of that to get the Q factor, but that's coming. Okay, now let's see. A tuner, this is what this is, a tuner circuit, and that's just what we expected. And notice that they do look different because one of them is we used a 100 ohm resistor, and one of them we used a 2200 ohm resistor. So let's go up here again. And we want, all right, so these you can just copy paste. They're exactly the same as before. Except now I'm adding them in I'm adding them in parallel. So there's that formula we looked at a little bit earlier. And that's Z2, don't forget. And then V1, V out over V in is, let's see, I8, yeah, so that's VC2. And then the bottom is the Z total. And I just have to add that ZLC I8 in quadrature with the resistor F8. And of course, you type them in, you do the fill handle, you make the graph, and you do it again for this guy. And you don't have to add your data. If you can wait, but if you have it, why not just go ahead and get it done? Up to you. Okay, so the pre-lab assignment is going to be the notes and submitting the spreadsheet with this graph. And yeah, and so but you won't have the phase angle, so that will stay blank for you guys in all three of these. What did I highlight? The phase? Yeah. We'll look at the phase angle for the analysis. Okay, there we go. I'll get this up on YouTube and post the assignment.